In section 11.2, we talk about an application of the chi-square distribution, and this is called the goodness of fit test. So a goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So in other words, we're trying to state whether or not a distribution that we are given follows a distribution that we believe that it follows, or if it's different. So we're going to see some examples of this as we go through here. First, expected counts is a term we need to talk about. So suppose that there are n number of independent trials of an experiment with k greater than 3 mutually exclusive possible outcomes. Greater than or equal to 3 mutually exclusive possible outcomes. So you have to have at least 3 different options that could happen when you do these independent trials. And they have to be mutually exclusive. Let P sub 1 represent the probability of observing the first outcome, and capital E sub 1 represent the expected count of the first outcome. And we're going to see how these things relate in a minute. P sub 2 will represent the probability of observing the second outcome, and E sub 2 will represent the expected count of the second outcome, and so on. The expected counts for each possible outcome are given by this. E sub I, which means just E sub some number, is going to equal mu sub I, which again is just mu for some number. Going back to these, how we've defined these, the first outcome, the second outcome. So this would be, I guess, the ith outcome. And the way you calculate that is you take n, which is the number of independent trials, times P sub I, which is the probability of a certain outcome, and you just multiply those together, and that gives you your expected count. And so we're going to see how that works in practice as we go on to our next problems. Example 11.1, there are a lot of words here, but here's what it says. A sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their grandchildren is different today than it was in the year 2000. According to the United States Census Bureau, in 2000, 22.8% of grandparents had been responsible for their grandchildren less than 1 year. 23.9% of grandparents had been responsible for their grandchildren for 1 or 2 years, or maybe between 1 and 2 years is a better way to say that. 17.6% of grandparents had been responsible for their grandchildren from 3 to 4 years. 35.7% of the grandparents had been responsible for their grandchildren for 5 or more years. If the sociologist randomly selects 1,000 caregiving grandparents, compute the expected number within each category, assuming the distribution has not changed from the year 2000. Our categories here, category 1 will be, I'm just going to describe it as less than 1 year. And then category 2 is going to be between 1 and 2 years. Category 3 is between 3 and 4 years. And then category 4 is greater than 5 years. So notice our categories are mutually exclusive, and we do have at least 3 of them. The percentage of each, so P1, according to this, is 22.8, so 0.228. P2, the probability of being in the second group, is, according to the information we were given, 0.239. P3, maybe I should be underlining these as I go. So here's the 22.8, here's the 23.9. 1 to 2 years, or 3 to 4 years was the 17.6, so 0.176. And then P4 is 35.7 right here. Okay, now notice this 1,000, that is our n value. N equals 1,000. So what we're supposed to do is compute the expected number for each category. So E1, The way we do that is we take the probability 0.228 and multiply by n, which is 1,000. And that comes out very nicely. So that's going to be 228 would be the expected count if everything stays exactly as it was before. E2 would be the probability of this category, 0.239 times 1,000. Multiply those together, you get 239. That would be the expected count for that category. E3, the expected count for this third category, 0.176 times 1,000. And that would be 176. And then finally, the expected count for the fourth category would be the probability there, 0.357 times 1,000. And that gives us 357. So very simple process of finding the expected count. You just multiply the probability you're given times n, and that gives you your expected count. Notice in this case, we didn't come up with any decimals, but you could have an expected count that was actually decimals also. So just be aware of that. They don't always come out quite this nicely. Our test statistic for goodness of fit test. So notice in the past, our test statistic was always a t-value or a z-value, I believe. I think those are the only two we've talked about so far. So here's our new test statistic. Let O sub I represent the observed counts for category I. So remember, we just talked about the expected counts. Now we're going to talk about, well, how many are we actually seeing if we actually count these people? E sub I represents the expected counts for category I. K is going to represent the number of categories. N will represent the number of independent trials of an experiment. And so all that is our setup. Let the formula chi-square equal the sum of all the OI minus EI values squared divided by EI. So in other words, we're going to add up, or we're going to subtract and square and divide, and then after we do that, for each category group, we're going to add up all those values. That's what the sigma part means here at the beginning. Now, again, we're not going to have to do that. We're going to have to do very limited math. We will have to do some math, but we're going to let the calculator take care of a lot of this for us. So approximately this follows the chi-square distribution with k minus 1 degrees of freedom. And remember what k means, even though I forgot to italicize it there. K represents the number of categories that we have. So in our previous example, we had 4 categories. So k minus 1 would be 3, and that would be the degrees of freedom. Again, provided that all the expected frequencies are greater than or equal to 1. Another criteria is that no more than 20% of the expected frequencies are less than 5. So here are the steps for hypothesis testing with our goodness of fit test. Determine the null and alternative hypotheses. That sounds familiar. So H sub 0, the null hypothesis, is that the random variable does follow a certain distribution that we're given. So in other words, in our previous example, it would be all those percentages that we're given. We are assuming with our null hypothesis that the actual counts, the observed counts, are going to be the same as the expected counts, the same as those percentages. H sub 1, the alternative hypothesis, is that the random variable does not follow the distribution. So it's very easy to set up our null and alternative hypotheses here in this case, because the null hypothesis is always that these two things are equal. The alternative hypothesis is always that they are not equal. Number 2, decide on the level of significance alpha depending on the seriousness of making a type 1 error. Step 3, note here that if the requirements in step 3b are not satisfied, one option is to combine 2 or more low frequency categories into a single category. So we're going to see what 3b is in a second, but that had to do with the fact that all of our expected counts had to be bigger than 1, and we couldn't have more than 20% of them that were less than 5. So part A, calculate the expected counts for each of the k categories. The expected counts are, if you remember how we just did that, it's n times the probability for each of those categories. And as the number of trials, P sub I is the probability for the ith category, assuming that the null hypothesis is true. Part B, verify that the requirements for the goodness of fit test are satisfied. And these are the requirements. All the expected counts are greater than or equal to 1. And then 2, no more than 20% of the expected counts are less than 5. If we don't have this, remember what they state right up here. All we have to do is combine some categories. That way, if we combine the categories, we can find out if this will actually work out for us. But then you won't have expected values less than 1, and you don't have to have 20% of them that are, you won't have 20% of them that are less than 5. Part C, compute the test statistic and again, we're following that formula. And again, some of this we'll have to do, but some of this we'll be able to just do with the calculator. Step 4, and we are going to, again, focus on the p-value approach as we have done previously. So A, compute the p-value from our chi-squared goodness of fit test. GOF test is how that is labeled on our calculators, I believe, if I remember correctly. Compare the p-value with alpha. If p is less than alpha, we reject the null hypothesis. And remember, that means there is enough evidence to support the alternative hypothesis, and the result is statistically significant. If the p-value is greater than alpha, then we fail to reject h sub 0, the null hypothesis, and there is not enough evidence to support the alternative hypothesis. And then finally, step 5, as we have been doing previously, make a conclusion regarding the claim. And that means we're going to interpret this in context of the scenario that we were given. Let's look at the calculator steps to do this. So first, number 1, enter the observed counts in L1 and enter the expected counts in L2. So we are going to have to calculate these expected counts. And we will put them in L2 under our stats menu, and we'll put the observed counts in L1 under our stats menu. Then we're going to press stat and go over and highlight tests, and we are going to select option D, which is the chi-square goodness of fit test. And then we will enter L1 for the observed category. We'll enter L2 for the expected category, and then enter the appropriate degrees of freedom following the DF option there. Remember, the degrees of freedom is always 1 less than the number of categories that we have. Then we highlight either calculate, calculate or draw. I just crossed that off evidently, but we're going to do calculate and we're going to press enter. So example 11.2, continuing with example 11.1's information, the sociologist wishes to determine whether the distribution for the number of years caregiving grandparents are responsible for their children is different today than it was in 2000. The sociologist randomly selects 1,000 caregiving grandparents and obtains the following data. Test the claim that the distribution is different today than it was in 2000 at an alpha equals 0.05 level of significance. So here's the information. We had already figured out these expected counts previously. So those are the ones that we did in example 11.1. Let's go ahead and state our null hypothesis, which in this case is more words than anything. So the null hypothesis is the distribution follows the percentages from the year 2000. Okay, and then that means, I'll switch colors here, then the alternative hypothesis is the same thing, but it's going to be that it does not follow that distribution. So what we're going to do is we're going to turn on our calculators, we're going to go to stat, we're going to go to edit, and for L1 we will put in the observed values, so 252, 255, 162, and 331. What just happened there? Okay, let's clear that off. 252, enter. What's going on here? Oh, clear, enter. Somehow I got up on the top. Okay, 252, enter. 255, enter. There we go. 162, enter. 331, enter. So those are the 4 categories for the observed counts. Here were our expected counts that we calculated earlier, 228, 239, 176, and 357. Okay, so we've entered those in. Now we're going to go to stat. We're going to go over to tests. And remember, we have to go all the way down to D. It may be a slightly different one, but we're going to see this. Let me go down a little further so it's kind of in the middle. So we're seeing the chi-squared GOF, goodness of fit test. That's the one we're going to choose. And notice the observed on mine here already has L1, and that's what we want it to be. If it doesn't say L1, you're just going to push second 1, and that will change it to L1. Second 2 would be L2. Now notice the degrees of freedom, it has 5. I don't know if that's one I used previously or if that is just a default value, but we do not want it to say 5. We want to count our number of categories here. And we had 1, 2, 3, 4 categories. So K is 4. And the degrees of freedom is always going to be K minus 1. So in our case, the degrees of freedom is going to be 3. So we have to make sure we choose the correct number, because if we don't, we're not going to get the correct answer here. So the degrees of freedom is 3. We're going to calculate. And we get, again, when they ask for the test statistic, our chi-squared value is, from right up here, 6.60. Remember, that is always positive. So if you get a negative number somehow, you did something very wrong. Our p-value is 0.0856. Okay. Oh, and by the way, this was the claim. The claim is that it was different, right? And notice we've got our degrees of freedom and our other stuff there. We were testing at an alpha equals 0.5. So since p is greater than alpha, our conclusion is that we will fail to reject the null hypothesis, which means if I write this out in a summary form, I'll put it up here at the top since I kind of ran out of space at the bottom. If we fail to reject, there is not enough evidence to support the claim that the distribution is different. Okay, so again, most of the steps are going to be the same. It's just we're using a different test and we're getting some different information to begin with. That is the end of section 11.2. That's how you do a chi-square goodness of fit test. And remember, that test is used to help us determine if the distribution that we have in our sample follows the distribution that we believe it should follow. And so you have to be given the original distribution, and you're going to match up the observed counts with the expected counts and see if they follow each other. So we've got 4 graded problems there. Again, if you get stuck, please don't be afraid to send me a message and ask for some help.